Okay, so Unit 8 is about Taylor expansions. Okay, and I've mentioned this name Taylor before in other lectures, and the idea of this expansions is to approximate uh, any function that we want by a polynomial at a given point, right? So the idea is that close in that particular point, the function is exactly equal to that polynomial, and close to that point, we choose that polynomial so that it is as similar to this function as we want. Okay, and uh, we'll go into more detail about how to create this polynomial, but you can see how powerful this technique is, because this means that for every function that is amenable to this technique, you can study its properties close, how it behaves close to a point, just studying this Taylor polynomial that approximates it, right? So we can think about limits or derivatives, things like that. The behavior of the function around that point is going to be determined by that polynomial, very equivalent to the behavior of the polynomial, right? But before we get on to the proper definition of the Taylor polynomial, we have to introduce some notation, right? So we've been talking about negligible sequences before, functions or equivalent, asymptotic equivalences, things like that, right? But in order to explore this in more depth, and we will need more depth in order to express the Taylor polynomials, we need to introduce more formal notation, okay? And this is what's called Landau's O notation, okay? The O notation, the small o. Okay, so coming back to our definition of negligible function, so f is negligible with respect to g when x goes to a, right? And a can be any number, including plus and minus infinity, if the limit when x goes to a of f divided by g is 0, right? So this is equivalent to the definition we had for sequences, right? Now the new thing is that now if f is negligible with respect to g when x goes to a, we write it like this, okay? And we read it: f is small o of g as x goes to a, okay? So that's going to be important, right? Let me first give you an intuitive understanding of this, then we'll go into some properties and then some examples, right? So the idea here is that when we go to x goes to a, right, the value of f is very small when compared to the value of g, right? So if you think about the limit when x goes to 0, a function f that for instance goes to 0 much faster than function g will be small o of g, okay? But we'll see some examples later, right? Okay, so there's a set of basic properties that are make this notation very useful to work with, and that's why we use them, right? And so there are 5 of them, and will be very similar to other properties that we've seen before. So for instance, that the first one is that the small o scales, right? So if we have f is small o of g when x goes to a, and we have a lambda, a real number, lambda, then lambda times f is also small o of g, okay? And the proof of this is easy, because if f is small o of g, then we have that the limit when x goes to a of f divided by g is going to be 0, right? But then if we multiply f by lambda, right, we multiply this by lambda, then this is still 0, right? Because the fact that we have multiplied this limit by a number doesn't change anything, right? Okay, so that's the first property. Let me think. Now, the second property is that this small o is additive, right? So if you have f1 and f2 are both small o of g as x goes to a, then the sum of them will also be small o of g, okay? So that means that if f1 and f2 are small o of g, that means that the limit when x goes to a of both of them divided by g, right, is 0, But now if we combine these two things, we have the limit when x goes to a of f1 plus f2 at x, right, divided by g. This is the same as the limit when x goes to a of f1 at x divided by g plus the limit when x goes to a of f2 divided by g. But this thing is 0, this thing is 0, so the sum is 0. Okay, so f1 plus f2 is small of g as well. Now, if we have that f1 is small of g1, right? Let's see this, and f2 is small of g2, then the product of f1 and f2 is small of the product of g1 and g2. Okay, and you see the idea here. We have we need to check that the limit of this product f1 f2 divided by the product of g1 g2 is going to be 0, right? But we have the limit of this is going to be 0, the limit of this is going to be 0, so all of this is going to be 0, right? Now the transitive property is that if we have a function f that is small of g, okay, this is equal to 0, and then the function g is small of another function h, okay, so these two limits are 0, then f is smaller of h. Okay, so we need to prove that the limit when x goes to a of f divided by h is 0, but then if we multiply and divide this by g, right, multiply and divide by g, again we have this limit is going to be 0, and this limit is going to be 0, so all of this is going to be 0, right? So f is smaller of h. And then finally we have the factorization property, right? So we have that f is smaller of g, so the limit when x goes to a of f divided by g is 0. And then we have that we want to prove that the limit when x goes to a of h f, okay, x divided by h g at x is going to be 0, right? But we can factorize and express this like this: h at x, f at x, h at x, g at x, right? And then h and h cancel out, and you have f divided by g, but we know that that limit is going to 0. Okay? So all of this, maybe this is very abstract, as we have been saying so far, but we have a very shorthand version of these properties that maybe it's helpful. Okay, so we have small of g multiplied by lambda is small of g, right? Small of g plus small of g is small of g. Small of g1 times small of g2 is small of g1 times g2. Small of small of h is small of h, and h times small of a of g is a0 times, h times small of g is small of h times g. Okay, so these are the common multiplications, or manipulations of the small o symbol that we will use over and over again, right? And so we'll leave them here while we work on our examples, right? So for instance, we have 3 real numbers, a, alpha, and gamma, and we know that gamma, alpha is greater than 0, right? Then x minus a to the gamma plus alpha is small o of x minus a to the gamma when x goes to a, right? Because the limit when x goes to a of x minus a to the gamma plus alpha divided by x minus a to the gamma, right, is just the limit when x goes to a of x minus a to the alpha, right? But x minus a alpha is greater than 0, so the limit of a polynomial, right, in this case, is going to be 0. Okay. So in practical applications, this means that, for instance, x squared is smaller of x, or x cubed is smaller of x squared, right? And also here you see small o of x squared, this is small o of x, so this is small o of x, so that means that x cubed is also small o of x. Sorry, this is when x goes to 0, right? Right, so that what this means is that x squared and x cubed and every other higher number x to the alpha when alpha is greater than 0 are small o of x. That means that they are going to 0, right, much faster than x. So see, you have here, if you think about the parabola goes like this, right? So they're approaching 0 much faster than the line, right? So that's how you need to think about these things, right? This is going to be very useful for computing limits, but also for many other purposes, right? Okay, so let's go for the next example. So we have alpha, again, a, alpha, and gamma real numbers, and we have alpha greater than 0. So we have 1 over x to the gamma plus alpha is small o of 1 over x to the gamma when x goes to a, right? Why? Because the limit when x goes to a of x to the gamma divided by x to the gamma, so this is when x goes to infinity, sorry. When x goes to plus minus infinity, yes. X to the gamma plus alpha, no, sorry, yes. Plus alpha is in the denominator, right? This is 1 over x to the gamma plus alpha divided by 1 over x to the gamma, so this is going in the denominator, sorry, in the numerator. So this is the limit when x goes to, and this is plus infinity or minus infinity of 1 over x to the alpha, which is 0, okay? So again, in other words, this means that 1 over x squared, for instance, is small o of 1 over x when x goes to plus minus infinity, right? Because that means that 1 over x squared goes to 0 much faster than 1 over x, and so forth for 1 over x to the 4th is small o of 1 over x, and so forth. Okay. Okay, let's see some more examples. We have that the sine of x is small o of the square root of x when x goes to 0, okay? So we know that the limit when x goes to 0 of the sine divided by the square root of x, we know that the sine is approximately equivalent to x, right? So this is the same as the limit when x goes to 0 of x divided by square root of x, which is, in other words, the square root of x. So this is 0, right? So this is because the sine is approximately equivalent to x, right? We know that this is approximately equivalent to x when x goes to 0. Then it means that we know x is small o of the square root of x, right? When x goes to 0, just like what we were saying before, right? That x to the gamma plus alpha is small o of x to the gamma when x goes to 0. So in this case, we have gamma equals 1/2 and alpha equals 1/2, right? So this translates into x equals small o of the square root of x when x goes to 0, right? And so x is small o of the square root of x, and also is sine, right? Because both of them are asymptotically equivalent. Right? So if two functions f and g are asymptotically equivalent, as we have been saying before, then that means that how to formalize this using small o is that we can say that f is equal to g plus small o of h, right? When x goes to a, when x goes to a, right? Or in other words, that f minus g is small o of h when x goes to a, right? So that means that the difference between f and g, or f and g are similar up to function h, that we can determine, right? Then that's what the things that we will see when we develop the Taylor polynomial, right? But this is kind of how you write about asymptotic equivalences with this notation, right? Okay, so another couple more examples. 1 minus the cosine of x is small o of x, right? When x goes to 0. Because the limit when x goes to 0 of 1 minus the cosine of x divided by x, we know that 1 minus the cosine is approximately equivalent to x squared divided by 2, right? So this is 1 minus, so it's minus, it's 1 minus the cosine. No, yes, sorry. 1 minus the cosine is equivalent to x squared divided by 2 divided by x. So this is the same as x divided by 2. So the limit of this is going to be 0, right? So again, 1 minus the cosine is asymptotically equivalent to x squared over 2 plus small o of x. Okay, this is what this means. Right? Okay. Okay, let's see a last example. Well, from the asymptotic equivalences and negligible relations that we had seen before, so we know that the logarithm of x to the r is negligible in comparison with x to the q. Well, that means that the logarithm of x to the r is small o of x to the q when x goes to infinity, right? Now the same goes for x to the q is small o of a to the x for any a that's positive and greater than 1, obviously, and this q and r positive numbers, and a to the x is small o of x to the x, right, when x goes to infinity. So you see how to write the things that we have seen in terms of negligible functions and asymptotic equivalences using the small o notation. Okay, and so let's see one practical example of the kind of things that we are actually going to see when we work in problems. Let's compute this product. 1 plus x squared plus small o of x squared, right? Squared, right? So then we have 1 plus x squared plus o's x squared, right? And then we have plus x squared plus x cubed plus x times o of x squared, and then plus x squared plus x cubed plus x fourth plus x squared times o of x squared, and then we have plus o of x squared plus x times o of x squared plus x squared times o of x squared plus o of x squared times o of x squared, right? Now we can use these rules to simplify things, right? So then we have let's see, let me write it here, right? We have one, let's collect the terms with the same powers, right? So this is 2x plus 3x squared plus 2x cubed plus, and then we have 1x to the fourth, right? And then we have o of x squared, small o of x squared here, and x times small o of x squared, right? But then x times small o of x squared, right? This is h times this is x times small o of x squared, using the last property is small o of x cubed, right? X goes inside multiplying. But small o of x cubed is small o of x squared, right? So then we can write this as small o of x squared, right? So this thing is small o of x squared. Now we can use the same argument. This thing is also small o of x squared. This thing and this thing, using the same argument, are small o of x squared. This is small o of x squared. Okay, this too. And what happens with this? This is small o of x squared times small o of x squared. Remember property C, small o of g1 times small o of g2 is small o of the product, small o of x to the fourth, but this is again small o of x squared, or in other words small o of x squared, right? So all of this combines to say that all of this is 1, 2, 3, 4, 5, 6, 7 times o squared, but 7 times o squared, or small o of x squared, sorry, is equal to small o of x squared using the first property, right? But we can also simplify this and this, because both these guys are small o of x squared, right? And we can't, once you have an expression with small o of x squared, that includes terms with x cubed and x to the fourth, right? So that you can't maintain these guys in the expression, because you don't know what's the coefficient of this in this, right? You're neglecting all of them from the start, right? So you can't keep them, right? Your expression can only reach up to x squared, and everything after that in terms of higher powers of x are going to be neglected and included in the same term, right? So the last thing is to collect everything. So everything is like this. This is the result of the square of this. 1 plus 2x plus 3x squared plus o of x squared, right? And this is the kind of, once you get used to these manipulations, you will get very fast in this, right? So you try multiplying this. Let me start doing again, right? So, because once you write one time small o of x squared, you don't need to write it again, right? So this is 1 plus x squared plus small o of x squared, right? And then we have x that multiplies x that multiplies x squared, and then we have x that multiplies x squared, that's x cubed, that's a small o of x squared, we don't really need to care about, right? And then we have x squared that multiplies 1, and then x squared, everything that it's going to multiply, it's going to be small o of x squared, so we don't really need to care about that. And then everything that multiplies small o of x squared is going to be small o of x squared. So we just have that, and from that we just collect the terms, and we're done, right? So this looks like magic, but it's actually well fundamented. We've seen these properties, and that's how it works. And as you get more familiar with this will become easier to you, right? So just one last note: if I say that f is small o of 1 when x goes to a, what I mean is the limit when x goes to a of f is 0, right? Because the limit of f divided by 1 is 0, right? So remember that. There's some handy way of express this. Okay, so that's the end of this video.